All right. Well, guys, I hope that you can all see me and hear me okay out there. It is 4 o'clock. I think I'd like to go ahead and get started here. Welcome on into Zoom one last time, hopefully, the last time. I should be coming back to Fullerton this coming weekend. And so by next Tuesday, the plan is to be back in class, which I know is much better overall. Although taking a little break, saving a little gas money this week, maybe not the worst thing. But yeah, I'm looking forward to being back in person with you guys. This is kind of challenging for me, just the setup of everything. And then on top of that, I went and got a vaccine today. They gave me a shot in my arm. My left arm is so sore I can barely lift it. So it'll be even harder for me to do this today, but I should be okay. Hopefully you guys can all see me and hear me all right. As always, if for some reason you're having trouble with either the video or the audio, I hope that you will let me know. I do have my chat window open, so I can keep one eye on that and take questions or comments that way. But you're also certainly more than welcome to use your microphone at any time. Don't be afraid to do that. We're all friends here. We're all just trying to learn. And if you have a question about something, there's a very good chance that somebody else has that same question, or at the very least, that they're just happy that somebody slowed me down long enough for them to kind of catch up a little bit. So feel free to ask questions as much as we need to as we go along here today. We are going to finish chapter 7 tonight. First of all, I also wanted to thank you for finishing the homework on Tuesday. I believe my grader got right on top of those, and you should have already gotten some feedback on the previous assignment. There is a new assignment that is actually due tomorrow night. It covers this stuff. That's kind of what I've recapped over here, talking about defective and non-defective matrices and how you find eigenvalues and eigenvectors of a matrix. So it's another really essential assignment with some very good practice for you. So definitely, I want you to work hard on that. I will have office hours tonight after my second class. And I'll also have some office hours tomorrow evening as well. So if you do have things that are unclear from the homework, by all means, feel free to stop by. And I'm even going to give you a chance tonight if you want to put some questions into the chat. I know on Tuesday I didn't really have much time, but I'm hoping tonight, if there are some questions on the homework that's due tomorrow, that I hope that I will have time today to maybe look at a few of those or give you some hints if you need them. But anyway, so that's homework number 18. That is due tomorrow night. The next homework after that one is going to be based on what we're going to talk about tonight, and it'll be due on Tuesday. So by that point, I'll be back in person, and we'll be able to work on that a little bit more easily. Does anybody have any questions about where we're at with those logistics here? This is week 11, guys. We only have 4 weeks left after this. It's going to go by so fast. So, but are there any questions about where we're at or what we need to be thinking about? Since I'm not hearing a lot, I'm not getting a whole lot of feedback in the Zoom chat either. I'm assuming you guys are hearing me and seeing me okay so far. So just let me know if anything changes on that. I am using my parents' internet to make this work, and that, who knows, that could always go out. Oh, the other thing was, I came back here. I wasn't expecting to come back, so I had to go buy some markers. So my parents thought that 4 markers would be enough. I'm down to my last marker. So if this marker runs out of ink, class will be over. I'm hoping it'll last for 2 more hours and then 2 more hours after that. But anyway, I'm down to my last marker, so we'll see. We'll see how it goes. I should have gotten a few more markers today, I guess. Anyway, that's okay. We'll make the best of it. So yeah, on Tuesday we talked about the idea of a defective versus a non-defective matrix. I don't want you to confuse the idea of defective and non-defective with invertible and non-invertible. They are 2 different things. They actually have nothing to do with each other. And on Tuesday, when I come back next week, we're going to do a group work where I'm going to really try to help you appreciate that fact. That defective and non-defective is a different issue completely from whether a matrix is invertible or not invertible, right? So let's not get them confused. I did put a reminder here. In both cases, you are talking about a square matrix. So A is an n by n matrix here in the way I've set this up. And it will be non-defective if it has n linearly independent eigenvectors, okay? And I kind of tried to rephrase that a couple of times on Tuesday to help us to maybe think about it a little bit differently. Instead of thinking of the entire set of all of the eigenvectors that you can make, I like to do it sort of eigenvalue by eigenvalue. So we go through each of our eigenvalues and we ask ourselves, do they pull their weight, right? Does every eigenvalue pull its weight? And what does that mean? Well, I tried to make that a little more precise as well. It says right here, for every eigenvalue lambda, the real issue comes down to whether the dimension of the eigenspace for that eigenvalue matches the multiplicity. So just to remind you again, m sub lambda stands for the multiplicity of the eigenvalue lambda. Right. Okay, so that's really what this is all about, okay? And of course, we can find the eigenvectors and eigenvalues for a matrix and then address this kind of a question. Is that matrix defective or not? So I hope you can see on my board here, I've got a couple warm-up practice problems to just kind of review this a little bit. We did this on Tuesday, but I just want to practice a little bit more. I've got a couple of examples of matrices here. I would just like to figure out whether they are defective or non-defective. All right. So let's just practice on the two examples. I'm going to start with the first one, number 1. And can everybody read this okay on this side? So far, so good? All right, perfect. So as you'll recall, the first thing we have to do for all of these problems in chapter 7 is find the eigenvalues of the matrix. Okay, so I'm going to try to find the eigenvalues. To do that, we have to take the determinant of, remember, A minus lambda I. So I'm going to subtract lambda off of the main diagonal of the matrix. So what I'll get in this case is the following matrix, 0, 0, and 8 minus lambda. So this is just the determinant for the first matrix A here. So what I'm writing down is A minus lambda I, right? That's this matrix here, A minus lambda I. And what I'm hoping to do is find the determinant. Now, I mentioned on Tuesday that I'm not such a fan of the arrow method for a 3x3 matrix in this chapter because you see these lambdas that are in the matrix? If you use the arrow method to try to solve for lambda, for a 3x3 matrix, you're going to get a cubic equation. Cubic equations are not so nice to find the roots of those equations. In other words, it's harder to find the eigenvalues, at least by hand, on a 3x3 matrix. However, there is something very nice about this matrix. Does anybody notice anything about the nature of this matrix or even the original matrix A that might be useful for us here? If you think of anything, you can use your microphone and tell me, or you can write it in the chat. Is there something nice about this matrix on this first warm-up problem? The bottom row has a couple of zeros. That's true. Anything else? Anything even a little stronger statement than that? Angelica is talking about the diagonal determinant. Why can I focus on the main diagonal here? What is it that's going to allow me to do that? I'm still looking for another word to describe this matrix. Edgar's got it, and Brighton. Thank you, guys. It is upper triangular. By the way, I really appreciate the chat comments. Thank you so much. Yes, this is upper triangular. And do you guys remember that when you take the determinant of an upper triangular matrix, you just have to multiply the main diagonal. So in this case, the main diagonal is 8 minus lambda times 8 minus lambda times 8 minus lambda. And what we have to do, as we've learned this week is set that determinant equal to 0. But you see, it's already factored. There's no need to multiply this out. In fact, you don't want to multiply it out. You just want to write down what the lambda values are from that factorization. And what you can see is, for this example, we get 8, 8, and 8. That's it. Those are the eigenvalues. So we're only going to have one eigenspace. And the multiplicity of this eigenvalue, right? I could write it maybe this way. It's a little bit clumsy. But the multiplicity of the eigenvalue 8 is 3. The same lambda shows up 3 times. So I want to remember over here, I've got to check, does the dimension of the eigenspace match that multiplicity? Okay, let's check it out. Okay, so to do that, I have to look at the null space. If I want to get the eigenvectors, right, if I want to find my eigenspaces, I have to take the null space of A minus lambda I. So I'm going to subtract 8 from the main diagonal of my original matrix, and I get a whole lot of zeros. I just get one pivot in the top middle entry, and everything else becomes zeros here. So again, this is just the matrix A minus 8I, right? So that's A minus 8I right there. Okay, and you can see that we will get 2 free variables. So let me call them X and Z, and I'm going to use R and T like I always seem to like to use to represent those free variables. From the top row of this matrix, the top row of this matrix actually requires Y to be 0. Right? Okay, and so if I was gonna bust out those variables and write down a basis for the eigenspace, remember E sub lambda is the notation for the eigenspace, then I'll get a set consisting of 1, 0, 0, and then when I bust out the T, I'll get 0, 0, 1. So I can bust out the R and I can bust out the T, but as you can see, there's only 2 variables to bust out. I only get 2 basis vectors. So what is the dimension of this eigenspace? It's only 2, right, guys? There's only 2 vectors there. It's only 2. It does not match the multiplicity, which was 3. Okay, so this is exactly what I'm talking about, guys. This eigenvalue did not pull its weight. It has a weight of 3. I see it 3 times here. But it only gave me 2 eigenvectors. So you know what? That means that this matrix is defective. This one is defective. We don't get 3 eigenvectors, 3 linearly independent eigenvectors. We only got 2. We only got 2. So that's the story of that first example. Any questions on that? Does that make sense? Okay, I'm gonna go ahead and erase this recap a little bit if that's all right. Hopefully you've got a chance to write it down already. I am recording this lecture though, guys, as always, so I will post this video into the class lectures in Canvas later on tonight if you missed anything. But let's go ahead and take a look at this second warm-up example now. Let's go on to number 2, and let's do the solution to the second one right here. Okay, so I have a 2 by 2 matrix this time. The entries are 9 and -5, and then 2 and 3. So I'm going to set up my determinant again. As before, I just have to subtract lambda off of the main diagonal of the matrix. So I'll go ahead and subtract lambda off of that main diagonal there. And this time it's only a 2 by 2. And for a 2 by 2 matrix, I can go ahead and just use the usual AD minus BC formulation of this. So I should get 9 minus lambda times 3 minus lambda, and then we would actually end up with a plus 10 on the end of that. And I'm going to go ahead, unlike my advice for a 3 by 3, on a 2 by 2, it's perfectly okay to go ahead and just expand it out. So we'll have lambda squared minus 12 lambda plus 37. If I do all the math, hopefully I got it correct. That's my characteristic equation, right? This is what we call the characteristic equation, which we're going to set equal to 0. Now, this one does not factor nicely. It really does not. Now, you can try to factor it nicely, but it won't happen. 37 just does not jive very well with 12 to make a nice factorization. So the good news, though, with a quadratic equation is that we can always get the eigenvalues by just using the quadratic formula. So I'm going to solve for lambda by using the quadratic formula, and I'll get 12 plus or minus the square root of 144 minus 4ac. So 4ac is actually 148, sorry, and I have to divide all of that by 2. All right, and that, give myself a little more room here. Got to get my heater powered up again here to help me erase the board a little bit more easily. But there's your lambda values. 12 divided by 2 is 6. And let's check out what's under this radical. So it's going to be 6 plus or minus. Look at this radical, guys. 144 minus 148. That's negative 4. So we have a negative number underneath this radical. The square root of negative 4. Remember that we have to use the imaginary number for this, the I value. So square root of negative 4 is actually 2I. But I have to divide that by 2 ultimately, because there's a 2 in the bottom of everything. So by the time we take 2I and divide it by 2, we'll just get I. These should be the eigenvalues. Now remember, guys, if you need to, check the fun facts. If I add up these two eigenvalues, I should get 12, right? Remember the trace 9 plus 3 here? That's the trace of the matrix, which is 12. So the eigenvalues should add up to 12. That's one thing that's very important. And if you were to multiply these two eigenvalues together, if you took 6 plus I times 6 minus I, you would get 37. Yeah, which is actually the determinant of A. And this is the other fun fact. So I'm not writing the fun facts down again at the moment, but those two fun facts that we emphasized on Tuesday are always helpful. We can always use those, and I definitely encourage it. Okay, let me well, let me ask you a question. Do we know if this matrix is going to be defective or not as of yet? Can we say already? The first one was defective. I just want to remind you, why was that? The first one was defective because the eigenvalue lambda equals 8 did not pull its weight. There were fewer eigenvectors produced than the number of repeats up here. 3 repeats and only 2 eigenvectors, right? But take a look at this. Is there any repeat eigenvalues here? Be careful, these are not the same, are they? 6 plus I and 6 minus I are 2 different lambdas. They are different eigenvalues. There's no repeats. And if an eigenvalue doesn't repeat, guys, if the eigenvalue doesn't repeat, then of course it will pull its weight. Yeah, it will definitely pull its weight. I already know that this one is non-defective. I already know that this is non-defective because I'll just add a little reason here for you. Since A has no repeated eigenvalues. No repeats sort of means there's no multiplicities there. There's no multiplicities. Okay, let's come back over here. Technically, we are done with it. This question just asked us, is the matrix defective or not? We already know that since there's no repeats, that it is non-defective. So we could stop, but just as a follow-up, I'd like to find bases for these eigenspaces. So let me just put that over here. So just as a follow-up question, let's find bases for the eigenspaces of this matrix A. I'll just write down the matrix again, 9 and -5, and then 2 and 3. Let's just do that. So we already have the eigenvalues. So I'm just going to focus on the eigenvectors now. Let's look at the first eigenvalue. So we practiced imaginary numbers, right, on Tuesday? So tonight we're going to practice again. This problem involves imaginary numbers. And so we have to work on this one using null spaces as usual. So I'm going to take the null space. It's the null space of what? Let's remember, it's the null space of the matrix we get when we subtract lambda off of the main diagonal. So I'm going to subtract 6 plus I off of the diagonal of A. So if I do that, I should be left with 3 minus I and -5, and then 2, and then -3 minus I. Something like that. So you just have to be comfortable with imaginary numbers showing up in your null space matrix here. But let's just remember how the flow of thinking went for this on Tuesday, because we had one like this on Tuesday also. The point here is, guys, that this matrix cannot be invertible. And that actually means that if we did EROs right now, which I'm going to highly discourage, if at all possible, do not do any EROs. Okay, if we did EROs right now, we know that we would get a row to get zeroed out. And it actually doesn't matter which one. These two rows are multiples of each other, even if they don't really look like they are. I know it's not obvious, but just the way multiplication of imaginary numbers goes, sometimes those calculations camouflage or hide the relationships between these rows. But we know the theory. The theory of this material is that we had set this determinant equal to 0 over there. And that means this matrix is not invertible. So if I do EROs, something's going to get zeroed out. And I'm just going to make a choice. It doesn't matter which row we sort of zero out, but I'm going to cross off a row, which basically means I'm zeroing it out. Now, obviously, if you crossed off the other row, you would get a different answer. At the end of the day, you'll get a different basis than I will. But remember, there are many correct answers, right? So you shouldn't be nervous if you check the back of the book and you're like, oh, their basis is different than my basis. That's not necessarily a problem. That's actually not necessarily a problem. So this is all that we're left with. And I'd like to remind you, on Tuesday, I explained this thing called the A-B trick. When I have just a single row with two numbers in it, and I want to write down a eigenvector. In fact, we can go right away and put down our basis here. The basis for this eigenspace corresponding to 6 plus I. There's an easy way to do it, guys, without having to do any back substitutions and setting up free variables, which is, do you remember how that worked? You swap these two numbers, right? You swap them. So you put the second one first and the first one second, and then you do a sign change on either one of them. So I'm going to put the 2 down here. And the -3 minus I, I'm going to put it in the first slot, but I'm going to do a sign change on it, which means it becomes 3 plus I. That's the answer. That is the answer. Or an answer, I should say. That is a correct answer. Edgar's asking, do they have to be presented as columns in your basis? They don't have to. You could write them as rows if you want, but I do tend to like to write my eigenvectors as vertical columns. Basically, because if you remember the most important equation in chapter 7, which is this one. AV equals lambda V. In order for that to make sense, the vectors have to be those eigenvectors, they do have to be presented as columns in order for the matrix multiplication to make sense. So I prefer to write them as columns. I would not ding you for writing them as rows, but I think you'll be happier in the long run if you are thinking of them as columns. It makes more sense that way. Okay? It's a good question. Does anybody else have any questions so far? Okay, well, this is just one of my eigenvalues. Let's keep in mind that we have another one, which is 6 minus I. And so here's the thing, and I got a little bit rushed on Tuesday. We could set up another null space and do the same thing, cross off a row, and then do the AB trick, and we'll get the answer in like literally less than a minute. But I can actually get the answer in less than 10 seconds. We can get it even faster than that, because I mentioned on Tuesday that when you have the complex conjugate pairs, so this is like A plus BI, and then here we have A minus BI. When you have these pairs of complex numbers that show up as eigenvalues, you can focus on just one of the eigenvalues. In this case, I chose to focus on 6 plus I, because the eigenvectors for the other one will automatically be expressible once we've done the first one. So let me show you what it is. We can write the answer down immediately. So the basis for the other eigenspace, I wrote this down, but I was kind of in a rush, so I'm not sure if I made my point as clearly as I would have liked. But the way that you write down the basis for the other eigenspace, just to remind you again, this is 6 minus I. The way you do that is you just take the eigenvector that you already came up with and you conjugate it. Every single entry gets conjugated. So 3 plus I, we're going to change that. We're going to conjugate it to 3 minus I. The 2 is not an imaginary number at all. So in the second slot, we don't do, when you're conjugating a real number, nothing happens. So it just stays as a 2. And so this would be the answer right here. Okay, so there you have it. That's without even taking a breath, you can write down the other the basis for the other eigenspace just by conjugating the basis that you got for the first one. Yeah, so that's kind of nice. Everybody with me so far? Any questions? Okay, well, there is a question that we probably should have somewhere along the line. Maybe you already were thinking of this on Tuesday, but if not, we're going to think about it tonight for sure, which is, why do we care about this? Who cares if a matrix is non-defective, right? What's good about that? How does that help us? It turns out that it's an extremely important thing. When a matrix is non-defective, you might remember I used another word for that in my definition on Tuesday. We also would call this kind of matrix diagonalizable. So in our 2 warm-up examples today, the first matrix was not diagonalizable because it was defective. Okay, the first warm-up example was defective, so it's sort of the end of the story. Nothing more to say about it. But this one was non-defective. And another way of explaining what non-defective is that it means that the matrix is diagonalizable. And I would like to take a few minutes and explain what's so nice about that. And that is this last section in chapter 7. We're only doing 3 sections in chapter 7. And so this is called diagonalization. So 7.3, this is what you're going to be doing homework on for next week, diagonalization. And this is going to give us some insight into what is so great about having a non-defective matrix. So let's assume, for the purposes of this section, that A, which is n by n, is a non-defective matrix. i.e. diagonalizable. So let's suppose that A is a diagonalizable matrix. Now, remember the definition of that is that means that, what does that mean again? So thus, A has n linearly independent eigenvectors. That was one way of thinking about it. Did you notice, by the way, that that did happen here on this second warm-up problem? We have 2 eigenvectors. N is 2 for the matrix in warm-up number 2, right? So the number of eigenvectors that we obtained in total matches the size of the matrix. So we have n of these. Let's give them names. Let's make a set of them. Let's say V1, V2, and ... up to Vn. Okay, so those are my n linearly independent eigenvectors. And let's remember that there obviously has to be an eigenvalue associated with each of those. Let's say λ1, λ2, and so on. And the last one is going to be λn. Can you guys all see that down there? λ1, λ2, all the way down to λn. So there's always, you always have corresponding eigenvectors that go with the eigenvalues. Okay, let's come back over here where I have some more space to write down the next part. Okay, so I'm just setting this up again. And the question is, well, what's so great about this? If A is diagonalizable, then sure, we have n linearly independent eigenvectors. But what's so great about that? Well, here's what we're going to do. We are going to form the matrix. I'm going to call it S. And S is the matrix where the vectors are laid out in columns, V1, V2, all the way up to Vn. I'm just going to make that matrix. So I'm going to form this matrix. You are going to want to know how to do that. Notice that this is going to become an n by n matrix. This will make S into an n by n matrix. All right, now what I want to do is I would like to do a calculation. I'm going to take A, I'm going to take the matrix A times S. Now, you may not have any reason to believe why would we be doing that, but I'm going to show you something kind of cool happens. Okay, so when I do this, I'm just taking A and I'm going to multiply it by this matrix whose columns are the eigenvectors. So I just put that there on the first step. I can write that as A times the matrix S as such. Now, when I actually get into doing this calculation, when I actually start doing this calculation, remember that we will be doing dot products of the rows of the first matrix with the columns of the second matrix. So you're actually going across the rows of A and then down the eigenvectors. So if you think about how that calculation will work out, ultimately the first column of this is going to be AV1. And the second column of this is going to be AV2. And ... The last column is AVN. Okay? So again, bear with me because something really cool is going to show up here in a minute. So the matrix A just basically multiplies each column as if it was a separate calculation. And so this is what we're going to have here. What is AV1? And what is AV2? Remember that these vectors, the V1, the V2, and the V3, those were the eigenvectors. And the corresponding eigenvalues are these lambdas. Does anybody remember the most important equation in chapter 7? I did manage to put it on the board here. It's on the top of the left side. if you take the matrix times an eigenvector, you can think of it as just lambda times that eigenvector, can't you? What that says, and that's what I see over here. I see AV1, well, that should just be lambda 1V1. AV2, that should just be lambda 2V2. And so on. I'm going to do that. I'm going to go ahead and put that in here. I mean, this is a very important equation. I keep harping on it. And here we're going to use it. All the way across. See if I can stretch my arms. All the way across like that, right? AV1 is equal to lambda 1V1. AV2 is equal to lambda 2V2, and so on. What you guys might notice here is that the matrix we now have on the right side is actually very similar to the original matrix S, except that each column has gotten multiplied through by one of these lambdas. I just want to show you something. Don't write this down, but I just want to show you something. If I take just any old random, let's just make it a 2x2 matrix. If I multiply it on the right by a diagonal matrix, let's say we got 5, 0, and 0, 8. If we actually just do this multiplication, so we go take the dot products of the rows of the first matrix with the columns of the second matrix. If we do this calculation, 5a plus 0 goes here. 0 plus 8b goes here. On the bottom row, 5c and 8d. Look at that. Look at what just happened. The columns of our random matrix got scalar multiplied by the values along the diagonal of this matrix on the right. That is actually always going to work out like that. What I can imagine is that we took this matrix F and we multiplied it on the right by a diagonal matrix that scaled these columns by these different lambdas. Right? That's the point. If you believe my calculation here, which isn't too bad because there's some nice zeros in that matrix, you just end up multiplying the columns of the original matrix by the scalars on the diagonal of the second matrix. So I'm going to erase that now. And now let's come back. If we are comfortable with that, what I'm going to do is I'm going to rewrite this as the original matrix S, V1, V2, and so on, up to Vn, multiplied on the right by a matrix that is a diagonal matrix with all of the lambdas going down that diagonal. Wow, look at that. Look at that. What's happened here, guys? What has happened is that the S matrix has ended up on the left, and this matrix on the right is a diagonal matrix, which I'm going to call D, and this is going to be where D is equal to the diagonal matrix with the lambda values going down the main diagonal. And that's also an n by n diagonal matrix, right? Everything here is n by n. Everything is n by n here. Okay. Awesome. Is everybody with me? So I'd like to just summarize that really quick. So in summary, if you believe my little calculation over there, the summary is that A times S is equal to S times D. That's the summary. Right? We started with A times S. I did this calculation. I ended up with S times D. Now, D is just a diagonal matrix with the eigenvalues of the matrix going down that diagonal. And the S is just this matrix made out of those eigenvectors. It's really pretty cool. Now, I want to warn everybody. Everybody is awake out there, right? Can I just cancel those S's? If you could. if you could cancel those S's, you would be telling me that A is equal to D. That does not sound right. Because that would be saying that your matrix A is actually a diagonal matrix. And we've seen plenty of matrices already, both Tuesday and tonight, which are non-defective, but which are not necessarily equal to a diagonal matrix yet. So A is non-defective, it's diagonalizable, but that doesn't mean that A itself is a diagonal matrix, but it is clearly related to one. It is related to a diagonal matrix that has its own eigenvalues going right down the diagonal. It's pretty cool. Well, the real reason you can't just cancel the S, of course, is that we know that that involves using like the S inverse matrix. So I mean, I could try. I could put S inverse there on the right side of this thing, right? So A times S inverse would equal S times D times S inverse. But remember, you cannot switch the order of anything. So you could cancel the S with the S inverse. And so this would be correct. That is correct. You can write that down. This is a correct equation. However, you cannot cancel the S with the S inverse right here because the S and the S inverse are not right next to each other. Right? You can cancel a matrix with its inverse as long as they're right next to each other. But here they are separated by a diagonal matrix D that's in between. So you're not able to do that. Also, let's just come back here and try one other thing. I could try to cancel it from the other side. So I could put the S inverse on the left side. And see, the S inverse being next to the S, yeah, I can cancel that. But on the left side, now the S inverse and the S, again, I cannot cancel them from the other side. So these two boxes are the best that we can do, right? They're both correct. You should write them both down, by the way. And it's a little tricky. You have to sort of learn which side does the S go and which side does the S inverse go, all of that kind of stuff. But they're certainly both correct. Okay. Everybody with me? Actually, if you're really, really, really sharp on this, you probably should have a question for me. Which is, I'll just ask it of myself if you don't mind. I like to ask myself questions. I do it all day long, every day. I ask myself a question here. I started talking about S inverse as if I knew that S inverse existed. Let's just remember that not every matrix has an inverse. Not every matrix has an inverse. And so the question I want to ask is, how do I know that S has an inverse? I seem to be acting as if I know that already. And it is true that this matrix S that I have formed over here, it is true that that matrix is invertible. And therefore, when I start talking about S inverse here, it's really okay for me to do that. But remember, if the matrix is not invertible, then I cannot just talk about the inverse of the matrix. It may not exist. So my question is, why do I know that S has an inverse over here? I'm going to give myself some room on the other side to make a comment about that. So a quick comment about this, kind of a theoretical comment, but I just want to make a quick note here. I'll put a little star here. S is invertible, i.e. S inverse exists. The matrix is invertible, and so it has an S inverse because anybody know why? It has to do with exactly how S was created. I mean, look at the columns of S, right? I've got N columns here. Yeah, Antonio's got it in the chat. I've got N columns here, and look, what are those columns? Those are these eigenvectors. And what did we say about the eigenvectors? They are Li. So the columns of S are Li. Wasn't that one of our invertible matrix theorem statements? Remember the big theorem, part A, B, C, D, E, F, G, H, I, J, on and on and on. We had a long, long list. One of the things in that list was that for an invertible matrix, the columns of it should be Li. Well, I have formed S exactly by using those Li eigenvectors. So I'll just say because the columns of S, they are Li. So S is invertible, and so when I start writing things like this over here, where I'm using the S inverse on both sides, it really is legit. It really is legit. Okay, questions so far? Oh, I'm so stoked. I love this stuff. It's just, I can't get too excited here or this whole contraption of mine in the studio is gonna like fall apart. So I have to kind of keep myself calm down. But if I was in the same room with you guys, I would be bouncing off the walls like usual. This is pretty neat that when the matrix is non-defective, we can diagonalize it. We can diagonalize it. Let me show you a couple of examples now where we can actually do a problem or two that's based on this. And I'm going to phrase this example the same way that the homework for next Tuesday is going to look, just so you kind of get the idea. So let's just do an example here. For each matrix capital A, which is n by n, find invertible S and diagonal D such that S inverse times S, sorry, S inverse times A times S is equal to D. So for number one, I'm going to do the first example. I'm going to take A to be the matrix that we just worked with a few minutes ago. 9, -5, and 2, and 3. Okay, so let's do that. Oh, let me just mention, guys, that on the homework for next Tuesday, when they ask you this, I want to be clear that they're not actually asking you to find S inverse. It just says find S and find D. Now, it's true that according to my boxed equation, S inverse times A times S should be equal to D. That is right. But they're not actually making us do that calculation. We are free to just not calculate the inverse of S right here. Of course, we learned back in February, right? We learned how to find inverses of matrices. So it's not like we can't do it. But these exercises are not going to ask you to actually calculate S inverse or to do this multiplication. Sometimes I see people do this, both on exams and on homework. They'll find S, they'll find D, then they'll go on to find S inverse, then they'll go on to take S inverse times A times S, and guess what they'll get? They'll get D, which we already knew is what they were supposed to get, and they've kind of wasted a bunch of time. You don't need to do that calculation. The theory already guarantees that S inverse times A times S is going to equal D. So here the whole issue is just let's find S and let's find D. Okay, so I'm going to put the solution right over here across the way. Right across the way, because you know what, guys? Because we already did this example from earlier, so let's just say I'm going to say C warm up number 2. It was our second warm up example. And if anybody's wondering why did I skip warm-up number 1, it's because the first warm-up example was defective, remember? If the matrix was defective, then we can't do any of this stuff. So that's why we're skipping over the first warm-up problem and we're just gonna jump to the one that actually did come out non-defective. But guys, this is very, very easy. S is just going to consist of the, remember how I've still got it on the board up here. S has columns, which are the eigenvectors. So if you look back in your notes, we had 3 plus I and 2 for one of the eigenvectors. And then the other eigenvector would have been the conjugate of that, which is 3 minus I and 2. So that is S. And then what is D? D is the diagonal matrix that has the eigenvalues along the diagonal. So that would be 6 plus I, and then there was a 0 and a 0, and then the other eigenvalue would have been 6 minus I. Right? So that's the diagonal matrix D. Does that make sense? One thing to be careful about, the eigenvalues have to be lined up in the same order as the corresponding eigenvectors. So this is one correct answer, but I'm going to just say that we could give a different correct answer. And another correct answer would come if we put the second eigenvalue in the first column and the first eigenvector in the second column. We could do that. We could swap the two columns here, but if we did that, we would be required over here in the diagonal matrix D to switch the order of those as well. So just be really careful. I got two different answers that are both correct. But you must line up. What I'm basically saying, guys, is you must line up the eigenvectors in S with the eigenvalues from D. They're supposed to line up. In other words, they have to go in the same order. Okay. But you see, we already did all the hard work in the warm-up problem. We already have the eigenvalues and eigenvectors, so it's just a matter of writing down S and writing down D. Okay. Let's do a second one. Let's do number 2. Oh, this is going to be a little tricky. I want to use, I might need somebody to help me. I want to use an example from Tuesday. For this one, I'm going to use the matrix B that we used on Tuesday. I believe it was 2, -5, and 5. And then, can somebody help me? Does anybody have their notes from Tuesday?
There's a message for you on the message in the chat.
Oh, there's a question in the chat as well. We're using the bases to build S. Yeah, Edgar, that's correct. We are using those eigenvectors to build S. These, the V1, the V2, the V3, those are the eigenvectors which are coming from those bases that we had calculated. That is absolutely right. Absolutely right. I want to say, does anybody remember this matrix from Tuesday or have your notes? Oh, Antonio's got it in the chat for me. Thank you so much, Antonio. You're saving my life because I didn't have it out in front of me. This is what happens when I come home without my notes. I don't know if you remember this example from Tuesday, but what we found on this example is that the lambda values were 2, 2, and 4. And the corresponding eigenvectors, so for E sub lambda equals 2, I did write these down. So this part I already do know. We had 1, 0, 0, and we had 0, 1, 1. And then for the other eigenvalue, which is lambda equals 4, we had the vector -5, -1, and 1. Okay, so this is what we had. So I'm just going to say C notes on April 8th. That would have been on Tuesday. we did 4 examples, I think, A, B, C, and D, and this was one of them. So all I want to do here again, guys, on this one, is I want to write down S and D. I'm going to write down S and I'm going to write down D. So I'm going to go ahead and pick an order to do this in. Let's say I decide to do 0, 1, 1, and then -5, -1, 1, and then 1, 0, 0. That's my S. Can somebody tell me what my diagonal matrix D should look like if I chose my S like that? It's got to be a diagonal matrix. The entries of the diagonal are the eigenvalues. So would this be correct? 2, 2, 4? Would that be right? See, we have to make sure we line up the eigenvectors with the corresponding eigenvalues. The way I did it here, I just tried to sort of mess up the order a little bit. The eigenvector that corresponds to lambda equals 4, I actually put that in the middle column. So I should have been doing it this way, guys. I should have put the 4 here and the 2 there. Okay? Now, this is not the only correct answer. This is not the only correct answer, guys. You could shuffle these 3 eigenvalues any old which way you want, as long as you shuffle the corresponding eigenvectors in a compatible fashion. Is everybody with me on this? So you're going to get more than one right answer. Depending on what order you listed these columns in, that'll affect what order you list the eigenvalues down the diagonal of D. Okay, so that's important to keep that in mind. That's how that works. Are there any questions on this, guys? So this example comes from Tuesday. We did it on Tuesday. And guys, if the matrix is not diagonalizable, you can't do this. There is no S, there is no D, there is no diagonalization. You can't do it. You still might be wondering, some of you still might be wondering, who cares? Right? Okay, I can find S, I can find D. So what? Right? I would like to convince you even a little bit more. I'm going to just briefly mention an application here, and then we're going to take a little break, okay? Quick little application, and then we'll take a break. The point is, let's just recall that one of the equations that we derived a few minutes ago is that A is equal to SD S inverse. A is equal to SD S inverse, right? So then one thing that is kind of nice is that what if I wanted to take some big power of A? Let's say I wanted to raise A to the K power. Maybe K is some really big number. Of course, you could use a computer, but from a theoretical point of view, this is very nice if I just replace A with SD S inverse raised to the K. And now the question is, how can we simplify that? Let's be careful. Can we get anywhere with this? Let's just be careful. What is this really, guys? This is really, if I think about it, this is SD S inverse times SD S inverse times dot, 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 dot. And the last one, SD S inverse. Right? You have a bunch of SD S inverses multiplied together here on the right side. Do you see how, well, first of all, I just remind you guys, parentheses don't matter here. you don't really need those parentheses. I can just think of this as S, D, S inverse, S, D, S inverse, S, D, S inverse, and so on forever, right? K times. So this is really what it is. The point is here, guys, that although I cannot cancel the S inverse and the S right up here in the original equation, down here, the S inverse is next to the S in many places. And if it's right next to the S, then you can cancel it. And what ends up happening is you cancel all of these S inverse S combinations that are in the middle of this big long expression. And the only thing that survives is an S at the beginning, and then a whole bunch of D's, and then there's an S inverse at the end. And how many D's is this? There's going to be K of them here. And so this becomes S D to the K times S inverse. That's pretty nice. And what makes this nice, the reason that that's kind of a nice equation to have, guys, is that D to the K is just, so if you take powers of a diagonal matrix, by the way, over here on this example, if I don't write any numbers in there, you should just assume those are all zeros. Sometimes I'll leave those out and just focus on what the diagonal values are. But the point is that what you get over here, what you get over here for D to the K, when you power up a diagonal matrix, the calculation is super easy. And so all that you end up getting is lambda 1 to the K, and then lambda 2 to the K, and dot, 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 all the way down to lambda n to the K, zeros everywhere else. So that is really nice. You can take a large power of D very easily. Okay? So I don't know about you, but if I asked you to take the 2025th power of the matrix B, I would actually much rather take the 2025th power of D, because this has tons of zeros in it. When you power up a diagonal matrix, it literally just powers up along the main diagonal. You can check that out. It's a simple little matrix multiplication thing. So D to a power is pretty easy to do. And because of that, I can take the power of the original matrix by just using this equation. So really, what is the punchline here? The punchline is right here. A to the K is equal to S D to the K S inverse. That's really what I want you to see here. Okay. So, all right, I can take large powers of a matrix by using this diagonalization theory. If the matrix is diagonalizable, I see an easy way to take high powers of the matrix. You still might not be totally thoroughly convinced that this is a big deal, because you're like, oh, I can always just put this matrix into a computer and let it do the calculation for me. And you're right. You are right about that. But there are other applications that build off of this one of which is called Markov chains. It's also called Markov processes. And that's something that really is real world applicable. And it's something that statisticians especially are familiar with, people who work with probability and statistics problems. And I made a video about what Markov processes is. I basically made a little example of a Markov process for you, and I made a video of it. And I'm going to send it to you to watch this weekend. It's not very long, but I'm going to have you watch a little video about Markov processes. It's a really important application of diagonalization. It's not the only application, but it's another very nice application that actually builds off of this one. So Yeah, I hope that you're at least somewhat convinced that when a matrix is diagonalizable, life is good. Okay. You can do calculations much more easily with a diagonalizable matrix than with a defective one. Okay. Well, that's about all I've got for the first part of our class tonight. Does anybody have any questions out there? Tell you what, if not, let's take a 10-minute break until 5:15. And at 5:15, during this break, if you want to put any questions from the homework that's due tomorrow night into the chat from either section 7.1 or 7.2, feel free to do that. But at 5:15, we'll come back and I'll see where we're at with the homework. And then we're also going to start looking at chapter 8. We're going to go back to differential equations. So second half of the class will be totally different topic. I'll see you in a few minutes. Guys, if you're out there somewhere in the sound of my voice and you can hear me, just letting you know I'm going to start again in about another minute. So this is a good time to find your way back over to wherever you're watching this exciting, dramatic story unfold. And we'll get started in one more minute. All right, well, it's about 15 after 5. I think I'll go ahead and get your attention again here if I can. Did anybody think of any issues or questions about this diagonalization process here during the break? I know I erased everything already, but um, when you have a non-defective matrix, you can diagonalize it. You can find S and D that are associated with the eigenvalue eigenvector pairs. And those matrices S and D allow you to more simply do calculations that involve the original matrix A. So it's a really, really useful tool, and it's a very, very important part of linear algebra. I don't see any questions on the homework so far. I'll leave it at that for now. The homework for tomorrow night, I know it's a quick turnaround on it, but it's mostly computational. The conceptual questions were kind of addressed in the homework that you turned in on Tuesday. And so the one for tomorrow is mostly just getting your hands on these calculations to find eigenvalues and eigenvectors, much like the examples that we've been doing here this week in Zoom. So I'm hoping that they'll go okay. I will have office hours though, and I do want to reiterate, it's very important to work hard on the homework. That's where you really need to learn the skills, because later on, it's going to be sort of taken for granted that you already know how to find eigenvalues and eigenvectors of a matrix. So be sure to put the necessary effort into it, however little or much that is for you personally, so that you can go into the weekend feeling like you're pretty solid on chapter 7. Yeah, these first 3 sections of chapter 7. Okay, and I'll be around to help if you do have some questions in the meantime. But what I think I'm going to do with the last part of our class tonight is something I know we have been building anticipation for quite a while now, which is I want to finally bring us back to differential equations. Oh my goodness, when did we last focus on that? It would have been January, like the end of January, back in the dark days of winter. We were talking about differential equations. And we've spent a good solid couple months now totally focusing on linear algebra. Well, it is now time for some of our hard work to pay off. I want to see the fruits of our labor. I want to see what does all that linear algebra do for me in the real world when I'm trying to solve real world engineering problems or physics problems or chemistry problems or whatever have you, whatever the application might be. So we're going to go back to differential equations. Chapter 8 is called linear differential equations of order n. If the differential equation is not linear, well, then you're not going to be surprised that linear algebra isn't really going to help you with that. It's really designed to help us with linear differential equations of order n. So somebody should start their watch right now and see exactly how many minutes does it take me before I'm already talking about linear algebra again as being applied to this, right? So how long am I going to go before there's going to be something from linear algebra that gets brought up in front of us here? And I'll give you a hint, it's not going to be very long. Okay, so let's just see how this goes. I'm going to start with a little bit of notation. I'm going to remind you what this linear differential equation of order n looks like. But a little bit of notation here that we're going to use. I'm going to use I to denote some kind of an interval on the real line. So that's an interval on the real line. Just as an example, it might be some interval like a to b. Or it could be the entire real line, which would be minus infinity to infinity. Or there would be other variations of those that we could be talking about. But I is going to denote an interval on the real line. And then the next notation, and this actually has shown up in a couple of places in the book, but I haven't really emphasized it a whole lot. A C of I with a super zero on it is going to be the set of continuous functions f going from I to R. So that's just going to be the collection. Just think of this as all functions that you can draw from left to right without picking up your pencil. That's a continuous function. And all of those together as a set is going to be C0 of I. The next one is C1 of I. And this is going to be the set of all of the differentiable functions. I'm going to just use ditto symbols here, guys, to save some writing. Differentiable functions f going from I to R. And maybe we want to keep going and we want to go all the way up to, let's say, C super k of I. And this is going to be the set of k times differentiable functions from I to R. Okay, so again, I'm using my ditto symbols. What does this mean, by the way? What this just means is these are functions that you can take k derivatives of them without getting stuck, right? Without getting to a function that you can no longer differentiate. So these notations, they do appear in the book, okay? And I should mention that every single one of these, is everybody's stopwatch going? Every one of these is a vector space. Yes, there's the linear algebra. I knew it wouldn't take very long. Each one of these is a vector space. All of them are. They're all closed under addition. They're all closed under scalar multiplication. Exactly. Okay, and so with that, I'm going to make a definition now. And I'm going to define something called the derivative operator. So the derivative, obviously with differential equations, we're going to take derivatives. So I'm going to create something called the derivative operator. And this is going to be, this is D. So I'm going to use a capital D for this. So D stands for derivative operator. And it goes from C1 of I to C0 of I via D of F equals F prime. So that literally just means that this operator accepts a function F as an input, and we just simply, as an output, we take the derivative of it. Just one derivative, okay? Now, more generally, we can take higher derivatives. So more generally, we define, this is still part of my definition. This is still part of the definition. We're going to define d to the k. And this is going to be an operator that goes from c super k of I to c super 0 of I. And the formula here is going to be d of f equals k derivatives of f. So the derivative operator is just really taking derivatives. Oops, this should be d to the k of f equals k derivatives of f. So that is the derivative operator. Okay. I'm just introducing this. This is pretty much all just notation on the left side so that I can talk about my linear differential equations of order n. Before I get into the actual differential equations, I am going to make one more remark here before we get too much further. And that remark is that all of these derivative operators, which would be like d and d squared and d cubed and d to the fourth, all of those, so they are all linear. The operators, let's put this down, the operators d squared, d cubed, and on and on and on up to any power of d, let's say d to the k, those operators are all linear. Oh, so that means I'm talking about more linear algebra. I mean, when I say linear, right? I mean linear transformation. They are linear transformations. They respect addition and scalar multiplication. Let's just check that. Let's just check it for D. D respects addition. And you guys thought you weren't going to have to listen to me talk about linear algebra. Yeah, it's already here again. It didn't take very long. So D respects addition. What does that mean? Well, if I take D of f plus g, if I add two functions f and g together, and I take the derivative of that, well, that's just f plus g prime. That's how D works, right? The derivative operator just takes the derivative of whatever you give it. And that, of course, can be split apart. That is just f prime plus g prime. And that is d of f plus d of g. D of f plus d of g. So that is the equation that shows that D respects addition. Okay? And similarly, D also respects scalar multiplication. Let me just give you a quick note on that. This just takes one line to write it down. If I take D of, let's say, k times f, this is how scalar multiplication would work. The way you do this is, again, you just take the derivative of whatever you give it. So you plug in k times f. You're going to take the derivative of that. But as we all know from calculus, you can always pull constants out of the derivatives. So I'll go ahead and do that here. The k pulls out in front, and then we're left with just f prime, and that's just k times d of f. And so that's also a check on that. So D respects scalar multiplication as well as addition. And you'll remember, I hope, from chapter 6, that a linear transformation just has to respect the vector space operations of addition and scalar multiplication. We actually did this example in chapter 6. I just didn't use the D operator for it. But I certainly made the comment that Math 250B would not exist if this wasn't true. If the derivative operator did not respect the vector space operations, it wouldn't really make sense to do differential equations and linear algebra together. We would not do that. But because this derivative operator is linear, it does make sense, and we're going to see very quickly all of the applications that we get. The same calculation would work for d squared, for d cubed, for d to the fourth, for any higher derivatives that we might want to do. Those are also linear. So this remark at the top of my board here definitely stands, that all of these derivative operators, they are all linear. Okay, all of this is kind of the background for what I want to get to now, which is, what is this chapter about? We're just kind of introducing it right here. linear differential equations of order n. Now, believe it or not, way back at the start of the semester, I had you watch a video, I think even before the class started. There were some videos I had you watch sort of before we kind of got things going. And one of them was, I wrote down what a linear differential equation of order n looks like. This was back in January, and you may not remember it, so I'm going to recall it for you here. I'm going to recall what that looked like, because that's actually kind of an important thing. If we're going to talk about chapter 8, we have to know what is an nth order linear differential equation. So the form of an nth order linear differential equation. I got to give you the form here. I'm going to write it down. And if anybody remembers this from 3 months ago, I'll be really impressed. Okay, but let's just see. Maybe this will ring a bell. It was a naught of x times n derivatives of y plus a1 of x times n minus 1 derivatives of y. And we go on and on, dot, dot, dot. I'm going to step over to the other side of my board here so that I can write down the rest of it. A n minus 1 of x times y prime, and then plus a n of x times y equals, and I'm running out of room, but I'm going to squeeze it in here, f of x. It was written as capital F of x. So on the far right hand side there, I know that's a little hard to read. I ran out of room there, but that's just f of x over here on the far right side. Does anybody out there remember that by any chance? It's okay if you don't. Like I said, it has been a while. What I want to do with it though is, of course, what we're going to try and do in this chapter is we're going to learn how to solve these. You may remember back in chapter 1 when we were doing differential equations at the start of the semester, we only learned how to solve first order differential equations. Remember those? The Bernoulli equations, the separable equations, the linear equations, right? Those were all first order only. N equals 1. Here, I have an nth order differential equation, and it's linear, and we're going to use linear algebra to help us solve it, okay? In order to do that, the first step that I'm going to take right now is I'm going to try to rewrite this equation using my new D notation. Okay, I'm going to rewrite this in the D notation. So let's see if we can do that. Rewrite in the D notation, this derivative operator notation. And let's see if it makes sense. Again, I'm going to step over to the other side, keep you guessing where I'm going to be. I come over to this side for a minute, and I'm going to rewrite this in D notation. The other thing is when I write this down, I'm not going to write out all of the x's again every time. I'm just going to start off with, a naught, and then I'm going to go D to the n. Let's start off with some parentheses, actually. And then I'm going to do, so get yourself a big set of parentheses here, and then I'm going to put of y over here. Okay? And then on the right-hand side, we'll just put capital F. So let me get it started this way. The capital F of x is on the right side. And what do I have so far? So far, what I have here, guys, on the board is a naught times n derivatives of y, right? D to the nth of y. Right? Any power of d applied to a function just takes that many derivatives of that function. So here I have n derivatives of y, which is exactly what we wrote right here. Okay, and then the next term, let's put a plus. The next term would be a1 times d to the n minus 1. And we're going to go dot, 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 a n minus 1 times d, and then plus a n. I've got to try to give myself a little more room here. Sorry. I'm going to write this one more time a little bit better. So this is going to be plus dot, 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 plus a n minus 1 d plus a n. There we go. It's a little tight, but I hope that's legible. Okay. So this isn't really solving anything yet. I'm just rewriting my differential equation using the D notation. You can imagine distributing this y to all of the terms in parentheses on the left, right? So a naught times n derivatives of y plus a1 times n minus 1 derivatives of y plus dot, 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 right? And then we have a sub n minus 1 times y prime. D of y is just y prime, and so on. And this whole big thing in parentheses here on the left is itself a combination of the linear operators that I'm referring to at the top of this board. This is just a combination of those. And so I am actually going to call this L, right? And this whole thing, being that it is a combination of a bunch of linear operators, is itself still linear, okay? And so what this means is, thus, my differential equation is, you ready for this? I'm gonna just write it super, super easy. L of y equals F. All right, that is the condensed expression of this linear differential equation right here that we would have written. We would have written it out in January like this. At the start of the semester, I wrote it out using all this notation. Now I'm going to write it out this way. And the goal for us, guys, the goal here, what do you think the goal is going to be? I can't sit in front of my writing, sorry. The goal here, L of y equals F, the goal is going to be to solve for y. That's the unknown function, right? That's what we'd like to solve for. Solve for y. That's going to be the objective that we're going to have. Okay. All right. I think that's a pretty good start. Okay. So with that, any questions so far? Get some of this notation out of the way. We really won't be focusing on it very much, so it's not so important here. Just remember that the D is just the derivative operator. That's really what this left side of my board is mostly trying to say. Okay? Maybe I'll do an example. Let's just look at a quick example, see if this makes a little bit of sense here. So as an example to kind of kick things off, let's just let L be the following operator. I'm going to make it x minus x squared times d squared plus the sine of x times d plus 2x. All right, so let's just let that be L. And then I'm going to let y be equal to e to the 3x plus 9x. And all I want to do here, I just want to make sure everybody's following me, how this works or how these operators work. I just want to compute L of y for a minute. Just want to practice calculating what would L as an operator do to some function y. And I've even given us a specific function to try here. And this is completely computational. But basically what we're going to do when we want to know what L of y is we're going to, well, we're going to apply this whole big L. Let me just go ahead and write it out here. X minus x squared times d squared plus the sine of x times d plus 2x. All of that is going to get applied to e to the 3x plus 9x. So again, this is just L of y. Just writing it out so far. You see how this L is working? Here's the notation for L, right? A naught d to the n plus a1 d to the n minus 1. So this thing right here would be a0. This sine of x, that would be a1. And the 2x, that would be A2. Those are A0, A1, and A2 respectively. And the way that you calculate this then is literally just sort of term by term. Okay, so let's just start off. On the first term here, I have x minus x squared. And then what do I see next? I see d squared. D squared means two derivatives of whatever you're applying it to. So I'm going to write e to the 3x plus 9x with a double derivative on it. Two derivatives of that. Okay, and then the next term is sine of x times d of e to the 3x plus 9x. So that'll be e to the 3x plus 9x with one derivative on it. So I'm using the prime symbols for these derivatives. And then there is one more term. I'm going to have to go down to the next line here, which is where we take the 2x and we multiply that by e to the 3x plus 9x as well. Okay, so you're literally just taking various derivatives of y and plugging them in right there. And now we actually have to do the derivatives. So on the next step, we would have x minus x squared times, well, what do we get when we take two derivatives of e to the 3x plus 9x? I'm going to kind of do this in my head. If I take two derivatives of that, I'm going to pull down this factor of 3 a couple of times, and I'm going to get 9 e to the 3x, right? And the derivative of 9x, well, two derivatives of 9x is just 0, right? So I don't need that part. And then let's go on. Let's add to that sine of x times one derivative of e to the 3x plus 9x. That would be 3e to the 3x plus 9. And then the last term doesn't really need to be worked on at all. We can just recopy it. 2x plus the quantity e to the 3x plus 9x. There's no derivative being taken there. So this would be the answer right here. That's the answer. It's not really simplified. We don't need to simplify it. This is not a big thing that we're going to work on. But you notice in this differential equation, we had two derivatives to take, right? We had to take two derivatives here, and that's because I should make a note here. Note that n is equal to 2. This is a second order linear differential equation. Now, guys, even though it's linear, it is linear, but I just want to point out the actual coefficients, the A0, the A1, and the A2, they are functions of x that can be anything. So if you're sitting out there wondering, well, wait a minute, why is he saying it's linear? Sine of x is not linear. Sine of x is a trig function. You're right, but with respect to the form of a linear differential equation, the A0, the A1, the A2, those can be any functions of x. They don't have to be nice. They don't have to be limited in a certain form or anything like that. What the limitation is just on how these various derivatives of y are laid out into separate terms. That's what's important here. Right. So anyway, this is a linear differential equation, even though you see trig functions and exponential functions and things like that going on here, powers of x. But it is in the form of a second order linear differential equation. Any questions on that example? I still have not solved a differential equation yet. I just want to be clear. My goal is ultimately going to be to solve these things for the unknown function y. In this example, I don't have an unknown function. I actually gave you the function y, and I just said, let's just crunch some calculations. Let's just practice how these derivative operators work. And that was really the whole point of this first example. We still have not talked in detail about this goal of solving for y, and the honest truth of the matter is most of that is going to wait until next week. the big thing we're gonna do tonight, and we only have less than 10 minutes to do it, is to just kind of get set up with all of this notation, make sure we kind of have the proper framework for everything. So I'm gonna state another definition and theorem here, and then we might have time, I hope we'll have time to do one last example tonight. So here's a definition, I think I can put it right down here, which is given L of y equals F, which is the most, can I call this the most important equation in chapter 8? I think I will. L of y equals F, right? The associated homogeneous differential equation is L of y equals 0. That is the associated homogeneous differential equation. Essentially, you're just ignoring the capital F that's on the right-hand side, and you're focusing on the left-hand side. So this is the associated homogeneous differential equation. And the goal here is still to solve for y. I mean, this is a perfectly good nth order linear differential equation too. And we would like to solve for y. And here, the solutions for y form something nice. In this associated homogeneous differential equation, does anybody think they might know what I'm getting at? What is the set, what are those solutions actually going to consist of? Or like, what is there a name, something that we've learned in linear algebra that would be describing the solutions here for y? Edgar put the word null space in the chat, and he's really close. The only issue is there's no matrix here. When I think about a null space, I'm always thinking about a matrix, but was there something a little more general when we talked about linear transformations? Instead of talking about null spaces, was there something that was kind of in the role of the null space that could be applied to any transformation? It's not subspace. It's a word that starts with the letter K. I probably gave it away. Who knows? Yeah, Gwen, you got it. That's right. It's the kernel. Do you remember the kernel? Our good friend, the kernel. This was when you took T of V and you would set it equal to 0. You remember that? That's how you calculate the kernel, as you solve for V here. Well, this is kind of like the same type of equation, isn't it? Instead of a T, now I'm using an L. And instead of a vector V, I'm calling it Y. But other than that, this looks pretty good. This looks exactly like the kernel. And so, in fact, the solutions for Y form the kernel of L. Yeah, which is, we learned something about the kernel. It was a subspace of V. It is, so which is a vector space. Oh my gosh. Guys, if it's a vector space, guess what? It's going to have a basis and it's going to have a dimension. That's almost the first question I always ask. Oh, I have a vector space in my hands. What's its dimension and what's a basis, right? So this kernel of L isn't just this is not just some like random bag of solutions to this differential equation. These solutions are organized really nicely as linear combinations of a basis for this vector space. And not only is it a vector space, I can actually tell you what its dimension is. It is of dimension n, as it turns out. It is of dimension n. So the kernel of L, at least this equation, okay, at least this equation down here. Now I realize this is not ultimately the equation we're interested in. Ultimately, we want to work on a more general type of nth order linear differential equation. But at least in this case, if we focus on the associated homogeneous differential equation, we can really get our teeth into the linear algebra aspects of it. The solutions to this guy form a vector space whose dimension is n. So if I have a second order differential equation and I manage to find two linearly independent solutions to it, then those two solutions will be a basis for all of the solutions to that differential equation. It is so, I'm going to have so much fun with this. I've got to do it in person. And I am going to be bouncing off the walls next Tuesday about this. This is a big deal. We could not have done this, guys, in January. We had to go through the pain of learning about what a spanning set is, what a basis is, and how we can write all of our vectors in terms of a basis. This is exactly how the linear algebra is going to creep back up to the surface almost immediately as we start trying to solve these differential equations. So instead of trying to race through a bunch of stuff overtime today, as much as I really do want to, but now I have to wait for 5 days. But the reason that I'm willing to do it so happily is I'll get to do it in person. And it is much better in person to show you this. This is a big deal. Do not miss class on Tuesday, guys, please. You're going to love it. I'm going to love it, and I hope you will too. Does anybody have any questions before we bring down the curtain on this week of Zoom here? If not, I'm going to let you go. I really appreciate you guys being here tonight. Have a great weekend. Send me emails or stop by my Zoom office if you've got questions on the homework. And I will look forward to seeing all of you in person again next week, back in our usual classroom. Thanks so much, and have a great night, guys. Bye for now.